And welcome back to the morning show. We're having a few laughs during the commercial break, as we usually do at this time of day. It is coming up on 6:49, time for our Chemist Corner. Jesse Miller is back with us. Jesse, thanks for coming back.
Sure, it's great.
Orange and blue playing the home opener this weekend. You're keeping in the spirit with the colors today.
That's right. We usually do this this week in the chemistry labs, you know, to kind of get the students, you know.
Sure, get them fired up.
Fired up for it. And the funny thing about it in general chemistry, you do this as a demonstration, but we don't generally explain the chemistry behind it because it's more complicated than what they have the base knowledge for. But it is an interesting, oscillating reactions were discovered about in the 50s. And at first, they didn't believe, he couldn't publish it because nobody believed, thermodynamically, it shouldn't happen. Okay. But because of quantum physics and chaos theory, they were able to show that this indeed, if you want to think of an oscillating reaction like a pendulum on a pendulum, you know, as it goes back and forth, that's right. It goes back and forth. When it reaches this bottom spot, that would be the equilibrium, but it keeps on going because it has momentum, and then eventually it'll come to a stop. But there is no chemical momentum. Thermodynamics says once a reaction is thermodynamically at equilibrium, it stops. There's no free energy to cause it to go one way or the other. So they're like, this should not go back and forth. It must be you know, there must be some contamination or something like that. But because of chaos theory and some other things, you got to think of it more like the hands of a clock. As the clock moves around, every once in a while, the hands are together at noon, 1, 2, or 1:05, 2:10, 3:15. But there's still a motive force moving the clock hands around, so it doesn't stop at that point. So that is basically what's going on here. This is 3 solutions, colorless solutions. One is, this is an iodine solution. This is a peroxide solution. Not terribly exciting. And this is a starch solution with some malonic acid and some manganese sulfate. And when we add this, let's get this stirring up here.
Okay, now folks at home, what is in there? And
it's a magnetic stir bar. This machine here basically has another magnet that spins around.
Bottom.
That's right. And this is a stir bar. It's a magnetic bar, and because the magnet inside the machine is spinning, it causes this to spin. Oops. And we're turning orange, so we'll just get going here. Oh, I got 2 stir bars. There we go.
That was quick.
That's right. Normally we have the students singing, you know, hail to the orange, hail to the blue. You know, I'm not going to do that.
So it's just going back and forth?
That's right. It'll oscillate just back and forth, and it'll keep doing this until eventually, because this is a closed system, even though it looks like it's open, it's a closed system, eventually it'll reach a point where it'll just stop. Okay, because there's no more motive force to go. Now, if you were to keep feeding this constantly, you could get a very steady oscillation, and that you could set a clock by, for the most part, and that's why a lot of times they call this an oscillating clock. But it'll keep going, you know, hail to the orange, hail to the blue, and we get them all singing and things like that. So cool. It's a very fascinating reaction. This particular one, this orange and blue one, was a couple of high school teachers, Briggs and Rocher, excuse me, came up with this one. It was an adaptation of a couple of other ones that had been around for a while. But it was until the 70s that they figured out exactly how these things work, and they still don't know specifically the mechanics of a lot of these oscillating reactions. And they're very important in the body. We see a lot of oscillating reactions in the body, and so now they're using these oscillating reactions to try to study in pharmacology to try to figure out how, you know, certain drugs work on the body and things like that.
How things react. Now the magnet stopped here, is that?
Yeah, it's because I dropped the other magnet in there and it's jammed up.
Oh, okay. Because it won't move. You can stick your fingers in there.
Yeah. But this will continue to go even without being stirred, because I stirred it up. Yep.
About how long?
As you can see, 15 minutes maybe.
So we could like stare at it like a lava lamp back in the day?
Yeah, that's right, that's right. All right. You're always going back to those 60s and 70s.
I like those lava lamps. And we had vinyl records on earlier today. I'm going to go bust out the bell bottoms again.
That's right, the black light
I'm sure my dad has some I could borrow. All right, Jesse, thanks for coming in. 30 minutes from now, what are we going to talk about?
We're going to do some gaseous diffusion and talk about the relative speeds of different gases, and we have a demonstration, and I'll show that.
All right, we're going to have gas for you coming up in 30 minutes. Well, maybe. All right, but if you want to see a replay of this segment, learn how this oscillating orange and blue cool thing works, go to our website, illinoishomepage.net, click on the morning show, look under